So we have Colin Defant from Princeton University talking about symmetry of Narayana numbers and Rowvacuation of root posets.
All right, thanks. Thank you everyone for coming, and also thanks especially to the organizers for putting this whole thing together. I think the conference is extremely cool, so I'm really glad it got to happen. And this talk is based on joint work with Sam Hopkins. So I'm going to start with phi being some irreducible crystallographic root system of rank R with vial group W. If you've seen these words before, that's great, but even if you haven't, that's also fine, because I'm going to show you some combinatorial pictures on the next slide, and you can just think in terms of those combinatorial pictures. But it is worth saying just a couple words about what these things are. So an irreducible crystallographic root system, you can basically think is like a very highly symmetric finite set of vectors, and the vectors are called the roots of the root system. It's living in some Euclidean space, and the dimension of the span of these roots is called the rank, which is R. And the vial group is just the group generated by the reflections through the hyperplanes orthogonal to these roots. So it's some group that's acting on this root system. And if you draw just an arbitrary hyperplane through the origin, which doesn't intersect any of the roots, that'll separate your roots into the positive roots and the negative roots. I'll let phi plus be the set of positive roots. And there's a natural way of defining a partial order on the positive roots, which makes it into something called the root poset. I won't give the actual definition, but again, I'm going to give you some pictures on the next slide that you can think in terms of those pictures. So whenever you have a poset, you can talk about what are called its antichains. So an antichain of a poset is just a subset, so that no two elements of that subset are comparable to each other. The number of antichains of the root poset phi plus is called the W Catalan number, which I'll denote by cat of W. And the number of antichains with a fixed cardinality k is called the W Narayana number, nar of W comma k. And the reason these are called W Catalan and W Narayana numbers is because in the type A root systems, these are just the classical Catalan and Narayana numbers. Okay, so let me show you some pictures of what these actually look like. This is a picture of the type A9 root poset. Basically, all of the type A root posets look like this. Maybe I should say that there are 4 infinite families of classical type root systems. There's type A, type B, type C, and type D. And in each one of these cases, if I put a subscript on the letter, that's going to be the rank of the root system. But you can also think of it combinatorially as just the number of minimal elements of this root poset. So for example, here, the number of minimal elements of my root poset is just 9, and that's the rank of the root system. And again, all the type A root posets basically look like this shape, just different sizes. The type B and C root systems are different as root systems, but they have isomorphic root posets. So I'm just going to draw C5. This is what it looks like here. Again, the 5 is the rank of the root system, which is the number of minimal elements here. And you can basically think of this as I sort of just took the type A9 root poset and I kind of folded it over its central vertical axis of symmetry to get this half of it here, which is the C5 root poset. And then finally, there's type D, the type D root posets. This is what D6 looks like. Basically, think of it as I just took like C5 and I kind of added in these extra little white minimal elements. They form a little chain here, this little chain of white elements, and they're related to some of the other elements like this. And this is basically what all of the type D root posets look like, just different sizes. Again, the 6 is the number of minimal elements because there are 5 black minimal elements, but then there's also this extra little white minimal element there. Okay, so now.
Before you move on, can we, there was a question from Sasha in the chat. She was asking if the poset is ordered by adding simple roots, adding on simple roots.
I think so. I mean, one way I know to do it is just to say that alpha is less than or equal to beta if beta minus alpha is a non-negative linear combination of simple roots. So that's one way of thinking about it. Okay. So the W Narayana numbers have this symmetry property which basically says that the number of anti-chains of cardinality k is the same as the number of anti-chains of cardinality r minus k. And this is not at all obvious from the definition that I've given. One way we know this is true is because there are alternative ways of defining W Narayana numbers, but from the anti-chains definition, it's not clear. I'm going to let A of phi plus be the set of anti-chains of the root poset phi plus. And Panyushev was really interested in this symmetry property, and he was coming from an algebraic motivation where he was looking at things called ad-nilpotent ideals, which are certain ideals living in the Borel subalgebra of the semi-simple Lie algebra associated to the root system. The main point here is there's some algebraic motivation for looking at the symmetry. And he made this conjecture that there should be some natural involution, which we'll call P, which is defined on the set of anti-chains of this root poset, which realizes this symmetry in the sense that the cardinality of P of A is just the rank minus the cardinality of A for every anti-chain A. Now, such an involution sort of has to exist in the sense that we know these numbers are the same, so there has to be some involution with this property. But what's really going on in this conjecture is there's this word natural. And what we mean by natural is actually Panyushev listed out several very natural conditions that he wants his involution to satisfy. And so really what we're saying here is we want an involution that satisfies this important property and also satisfies these other very natural conditions, which I'm not going to list out. So there is something actually non-trivial about proving this conjecture. And Panyushev proved this conjecture in types A, B, and C. So if you care about the classical type root systems, the only one left is type D. But this turns out to be the hardest case. And the main punchline of the talk here is that Sam Hopkins and I have settled the conjecture in type D. And so I want to tell you about the involution that actually works. And in fact, this is going to be an involution that works in all of the classical types. This is called Rowvacuation. And this is a map that Sam defined in a previous paper. And you can actually define it on any ranked poset. So let me define it for an arbitrary ranked poset, capital P. Also, the name ranked, the word ranked here is not the same as the rank of the root system. They're just distinct notions of rank. So hopefully that's not confusing. But a ranked poset is just a poset that has a rank function. A rank function is just a function defined on the poset, which assigns each element a rank so that the minimal elements all have rank 0. The elements covering the minimal elements have rank 1. The elements covering those elements have rank 2, and so on. And you just work your way up. And I'm going to let capital R be the maximal possible rank of one of these elements. Now, if we take some element little p in our poset and some anti-chain A, we can do what's called toggling A at P. And basically what you do here, well, I wrote it out in symbols, but what we're doing is really, we're trying to transform A into some other similar anti-chain. We want to get some new anti-chain. And so if the element little p is in our anti-chain, we just take it out. Just get rid of p, and then we have some new anti-chain. On the other hand, if p is not in the anti-chain, we try to add it in. The only problem with that is that p might be comparable to something that's already in the anti-chain, in which case we cannot add it in because then doing so would result in something that's no longer an anti-chain. So if that's the case, we actually just don't do anything. We just leave A alone and don't change it. I'm going to give some examples of this on the next slide. So if it's not clear already, I think this will be clear when I do the examples. For now, let me just define tau bar sub I to be the operator that toggles at all of the elements of rank I, sort of simultaneously. Basically, you can toggle at all of the elements of rank I in whatever order you want, and the different operators that toggle at the different elements of rank I will commute with each other, so it doesn't matter which order you do it. And finally, Rowvacuation is this operator which says, first toggle at all of the minimal elements, and then toggle the elements of rank 1, and then toggle the elements of rank 2, and then 3 and 4, and so on until you toggle the maximal rank elements. So this is like one run through. But then you do the same thing again, starting with the elements of rank 1. So you do rank 1, then rank 2, all the way up to rank R, and then you do the same thing again, and so on until eventually you toggle all the elements of maximal rank. Okay, so this is sort of a lot of symbols. Let me go through an example that I think makes this clearer. Let's say we take our poset, our ranked poset, to just be this root poset of type A4. And let's take the anti-chain to be this set of 3 elements that I've circled here in blue. The first step of doing Rowvacuation is to toggle all of the minimal elements. So when I toggle this minimal element here on the far right, that is going to, well, that's in the anti-chain. So the rule for toggling, it says, just take it out of the anti-chain, just get rid of it. So I'm going to remove the circle around it. And then when I toggle this element here that's next to it, that is less than this element that's already in the anti-chain. So I can't add this element in, which means I don't do anything. Similarly, when I try to add in this element here, it's less than the elements already in the anti-chain, so I can't add it in, so I do nothing. And then similarly, when I try to add in this element, it's less than this element that's already in the anti-chain, so I can't add it in, so I do nothing. So after toggling these 4 minimal elements, I removed the circle from this one, and I did nothing with these 3, so I end up with this anti-chain here. Okay, so is that part clear? Because I think if that's clear, then we're going to be good from now on. Okay. So the next step is we do the same kind of thing, but we toggle the elements of rank 1. So when I toggle this element of rank 1, it's not in my anti-chain, so I try to add it in. And I succeed in doing so because it's not comparable to anything already in the anti-chain, so I just add it in. Then when I toggle this element here, it's in the anti-chain, so I take it out. And similarly, this element is in the anti-chain, so I take it out. And after I add this element in and take these 2 out, I'm left with this anti-chain. The next step was we toggle the elements of rank 2. When we toggle this element, it's bigger than this element that's already in the anti-chain, so we can't do anything, so we do nothing here. And then when we try to add in this element, we can, so we add it in, so we get this. And then we're going to toggle the elements of rank 3. There's just one of them at the top. It's not in the anti-chain, but it's comparable to the things already in the anti-chain, so we can't do anything, so we do nothing, and we're left with this. So that's one run through, but now we have to do the same thing again, starting by toggling the elements of rank 1. So we're going to take this anti-chain here and toggle the elements of rank 1. And I'm going to go through this faster now because I think maybe we're getting the feel of how this works. So we toggle the elements of rank 1 here, and we end up with this anti-chain here. Then we toggle the elements of rank 2, and if you do that, you get this. Then we toggle the element of rank 3. When we do that, we end up with this anti-chain. And that's the second run through. So now we do another run through where we start at the elements of rank 2. So now we toggle the elements here of rank 2, and we get this anti-chain. Then we toggle rank 3, and we get this one. The last step is finally we do one last run through where we just toggle the element of rank 3, and that does nothing in this case. And so we're left with this. So the entire process here is one operation of Rowvacuation. Okay? So notice we had this root poset of rank 4 because it has 4 minimal elements, and we started with an anti-chain of size 3, and we ended up with an anti-chain of size 1, and 1 is 4 minus 3. So that's sort of good because we're trying to prove this Panyushev's conjecture. It's not clear from the way I define this that this should be an involution, but it actually is an involution, and it ends up settling Panyushev's conjecture. In fact, it settles it in all classical types. So Mike Joseph and Sam Hopkins observed that this Rowvacuation map is actually the same as something called the Lalong-Crevra involution, which is an involution defined on dick paths. And dick paths are basically the same as anti-chains of the type A root posets. I'll give a picture on the next slide to show why that's true. And so together with Panyushev's work, this basically shows that Rowvacuation works as Panyushev's desired involution in types A and C. So the last remaining case was type D, which again is the hardest case. And then that's what Sam Hopkins and I proved. So we showed that Rowvacuation also works in type D. And the proof of this requires an intricate combinatorial analysis of how this Rowvacuation operation interacts with a similar operation called row motion. Row motion is basically what you get if you sort of did one run through here and you just stopped. So you didn't keep going. You just did one run through where you toggle the elements of rank 0, then 1, then 2, all the way up to the maximal rank, and then you just stop. That's row motion. And so we have to understand how row motion interacts with Rowvacuation on these type D root posets. And this involves looking at this intricate bijection due to Armstrong, Stump, and Thomas, which connects row motion with something called the Crevra complementation map. So there's sort of a lot of intricate combinatorics going on here, but the main point is that in type D, this works. And I'll also just mention that if you care about the exceptional type root systems, it turns out that Rowvacuation does not work in those cases, except for G2. It does work in G2, which you can check by hand, but it doesn't work in the other exceptional types, which I think is a little strange. So maybe there's some modification that works in the other types, but we know it works at least in type. Okay, So that's everything. And as I promised, there's this correspondence between anti-chains in type A root posets and dict paths. And basically it's given by this correspondence where the anti-chain labeled by the letters in thanks corresponds to this dict path that I've drawn. So that's all.
Last thing, Colin. Any questions for Colin? There's this one question in the chat that was not, and I don't know if it actually was answered or not, but what makes type D harder?
Okay, so that's a good question. Well, just a general rule of thumb, I think, is that type D is usually harder to deal with than A and B. One part of it is that, yeah, I mean, I don't have a very good answer other than just these extra elements are really weird. Because you've got this nice pattern going on from the type C root poset, and then you've just added in these new things, and that kind of just throws everything off when you do this Rowvacuation. Because this Rowvacuation is this weird process where you're doing all of these toggles, and it just kind of makes things work really strangely when you have these extra elements. I don't really have a good explanation other than that, but yeah.
Any other questions?
Does the homomessy that you're seeing of n over 2 extend birationally in the type D case?
Does it? So I'm not so sure of this. It might, but I'm not. Oh, okay. So basically, it might. I know that what Mike Joseph and Sam Hopkins were looking at in their paper was actually extending this Lalonde-Crevera involution to the birational setting. So definitely in type A, it does, because that was sort of the purpose of their paper, but their paper is very recent. It came out like in December or January. So I think if there is a birational lift of the type D setting, then it hasn't been done yet.
Any other questions? Okay. If not, let's thank the speaker again.